Up to now, interrupt structure is completed. Now let us see the question related to that. Here, question given. Consider the hypothetical CPU which supports 4 interrupts I1, I2, I3, I4 with the respective service times of 20 nanosecond, 40 nanosecond, 50 and 30. I1 has the highest priority, I4 has the least priority. Response time of an interrupt is 2 nanoseconds given. What is the range of time required to service the I4 interrupt when the interrupts may or may not occur simultaneously? So first thing, range of time. Range in the sense minimum to maximum. What is the minimum time required to service the I4? What is the maximum time required to service the I4 interrupt? That we need to find out. Okay, in the CPU 4 interrupts are there. Interrupts occurrence is either with simultaneously or without simultaneously. May or may not occur simultaneously. With simultaneously means all the interrupts are occurred at a time. Without simultaneously means only one interrupt is present at a time. You know? So minimum time possible when the interrupts are occurred without simultaneously. Only one interrupt is present, that itself a I4. Then it gives the minimum time. Maximum time is possible when all the 4 interrupts are occurred simultaneously. Accordingly, the priority, we are going to select the high priority interrupt. Is it okay? Right. Now, here, what will be the interrupt service time? What will be the interrupt response time? When the interrupt is occurred, at what time after occurrence, you know, when the interrupt is occurred, how much time is required to respond to the interrupt is the response time of interrupt. After sending the acknowledgement to the interrupt source, how much time is required to service the interrupt, or how much time is required to execute the interrupt subprogram is the service time. Response time means when the interrupt source send the interrupt request signal, how much time is required to send the interrupt acknowledgement signal to the interrupt source. How much time CPU is taking to send the interrupt acknowledgement signal to the interrupt source. That is response time. Delay between the interrupt request and interrupt acknowledgement. After receiving the acknowledgement, how much time is required to process the interrupt subprogram is a service time. Clear now? Right. Now total time equal to response time, let us denote RT, and service time, you denote with ST. This is the total time required to service the interrupt. Now, first minimum time required for I4. This is possible without simultaneous occurrence. Minimum time means only one interrupt is present. Okay, that is I4. Then to complete the I4, response time required, service time required. Response time 2 nanoseconds. I4 service time given in the question as 30 nanoseconds. So total equal to 32 nanoseconds. This is the minimum time required to service I4. Next, maximum time required for I4. Okay, this is possible with simultaneous occurrence. With simultaneous means all 4 interrupts present at a time. At a time 4 interrupts present. That is I1, I2, I3, I4. 4 interrupts. Clear now? So according to the priority, service them. highest priority is I1. So first I1 is serviced, that is RT and ST. Next I2 is serviced, that is RT and ST. Response time and service time. Response time and service time. Response time and service time. Is it clear now? Right. Now total value equal to 2 plus 20 plus 2 plus 40 plus 2 plus 50 plus 2 plus 30. Correct now? Now adding all the values. How much it is? 148. 30, 20, 50, 50, 100, 148 nanoseconds. Understand? So range of time required. Range of time required for I4 equal to 32 nanoseconds to 148 nanoseconds. Is it clear? So this is the way of solving the question. Right? I hope you understand the question. Range means minimum to maximum. Minimum is possible when the interrupts are occurred without simultaneous. Maximum is possible when the interrupts are occurred with simultaneous. Without simultaneous means only one interrupt is present at a time. That itself a I4. Minimum time is ready. Then maximum time is possible with simultaneous means all 4 interrupts are occurred at a time. Then service them accordingly the priority. Question indicating I1 is highest priority, I4 is least priority. That's what first we service the I1 and I2, next I3, last I4. So maximum time is I4. Maximum time. Answer is 32 nanoseconds to 148 nanoseconds. Right? Now see the next question. This is the next question. Read it. Consider 32-bit hypothetical CPU. Processor 32-bit. Word length is 32-bit. Right? Consumes 4 cycles for memory reference, 2 cycles for ALU operations, 0 cycles for register reference. Cycle time of a CPU given 2 nanosecond. Following code is executed in the CPU. Program is stored in the memory with starting address of 1000. So here code given. Code contains 6 instructions. Move, add, mull, move, halt. It is a combination of data transfer, data manipulation and a transfer of control instructions. Program is a combination of data transfer, data manipulation and transfer of control instructions. So that only given here. Understand? Move, data transfer, add, mull, data manipulation and halt, transfer of control with various addressing modes. Addressing modes covered here, instruction set also covered here. Okay. Also meaning of the instructions given here. Size of the instruction given. Size of the instruction given in words. This is the question. Now we need to answer the question by taking the 2 parts here. First part is if an interrupt occurred during the execution of a halt instruction, what could be the return address pushed into a stack? Interrupt occurred during the execution of a halt. Understand? So first of all, we should know the storage structure of a program. Storage structure. Here, memory is a byte addressable by default. Memory configuration is not given. So default configuration is byte addressable. Byte addressable in the sense cell size equal to 8-bit. Byte addressable. Cell size equal to 8-bit. Is it okay? Right. Now verify this. I1 instruction 1 2 word. 1 word size is how much? 32-bit. 32-bit means how many bytes? 4 bytes. Therefore 1 word instruction takes the 4 cells of storage space. It is a 2-word instruction. 8 cells of storage space required. 1000 is the starting address. 1000 to 1007. I2. 2-word instruction. So 8 cells of storage. By default, byte addressable storage, because question does not indicated the memory configuration. In a default configuration is byte. So 1008 to 1015, total 8 cells. Next I3, one word. One word means 4 cells. 1016 to 1019. Next I4, two words, 8 cells. 1020 to 1027. Next one, two words, 1028 to 1035. Next one word. One word means 1036 to 1039. Next one, sequence 1040 and so on. Clear now? So this is the program storage in the byte addressable memory. Is it okay? Now we are going to solve the question. Interrupt is occurred during the execution of halt. Now we need to take the interrupt execution process. You know? That means, see, here it is fetch cycle. After the fetch cycle, execution cycle. After the execution cycle, checking for the interrupts. Okay, if interrupt is present, yes, then service the interrupt. After the servicing, it will be moving back to fetch. If no interrupt, then also moving back to fetch cycle. So this only we discussed in the previous concept. Now apply. Here, halt instruction is fetched from the memory. When the halt instruction is fetched from the memory to CPU, IR, program counter is increments to sequential address. You know, I6 is the halt. When I6 is fetched, program counter holds the sequential address 1040. Clear na? Now this halt is undergoes execution. Halt invokes unconditional jump with the starting address of the halt as a target address. Starting address of the halt is 1036. That become a target address. Correct na? So because of it is an unconditional jump, without checking the condition, program counter sequential address is replaced with the target address. That is execution cycle of a halt. After execution cycle, checking for the interrupts. In a question indicates interrupt occurred during the execution of halt. CPU respond to the interrupt after completion of the halt execution. So after halt execution, when it is checking for the interrupt present. When interrupt present, immediately PC value will be pushed into a stack. What is the PC value? 1036 is pushed into a stack. Correct? Later, vector address is loading into a PC. This is the interrupt subprogram initialization, what we discussed in the previous concept. Okay. Now question is, what will be the return address pushed into a stack? Answer is 1036. Because of halt is a unconditional jump. During the execution cycle, program counter is updated. So that updated value will be pushed into a stack. So answer is 1036. Clear now? Right. Come to the next one. What is the program execution time? To find out the program execution time, let us take the instruction cycle. Fetch cycle and execution cycle. IF, ID, OF, PD, WB. OF source 1, source 2, WB destination. This is the framework known to you. When you are capable to answer this question, it shows the realization of all concepts what we discussed till now. Okay? interrupt covered, instruction set is covered, addressing modes are covered, instruction cycle is covered. Okay, right. Now fill the information. First instruction 1. Instruction 1. Instruction 1 is 2-word long. Instruction 1 is 2-word long. Here given. So that one memory reference to fetch the first word counted in the IF. Again one memory reference required after decoding the first word. Then it is a data transfer operation. Source and destination. Source addressing is memory indirect. 2 memory references. Destination is register addressing 1 RR. So no need of the source to, no need of the ALU. Source is the memory indirect, 2 memory references. Destination is 1 RR, register addressing. Next instruction length is 2-word. Therefore, I2, 1 memory reference in fetch, 1 memory reference in the decode. ID. Right? Next. It is also data transfer. Memory to register. This is direct addressing. This is register addressing. Therefore, here 1 MR for the direct addressing. Source to PD not required. 1 RR for the destination. Register reference. Next I3. I3 is 1 word long. 1 word long. Is it okay? Now, 1 memory reference counted in the IF, no memory references in the decoding cycle, then it is a ALU operation. Source 1, source 2, destination, all are using the register addressing mode. So 1 RR, 1 RR, 1 ALU, 1 RR. Clear? Next one I4. I4 is this. Multiplication. 2-word instruction. Multiplication. Source 1 is a direct addressing, source 2 is a register addressing, and destination is a direct addressing. Direct addressing means 1 MR. So here 2-word 1 MR, decoding 1 MR, source 1 direct addressing 1 MR, source 2 1 RR, ALU operation, then destination 1 MR because direct addressing. Next one. This is the I5. 2-word instruction, data transfer from register to memory. So this memory using the index addressing mode. Cleared? Now see this. I5. 1 MR. Again 1 MR counting in the decoding state. Then 1 RR, source is register. No need of the PD and ALU. No need of the source to and PD. Then destination. Index addressing. 1 RR, 1 ALU, 1 MR. Is it clear? Okay. Next I6. It is 1 word long. 1 MR. So it is a halt. Decoding is enough to execute the halt. No need of the memory references with respect to remaining portion. This is the style of executing the code individually with respect to every instruction. Now we need to find out the program execution time. Program execution time equal to how many memory references? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. 16 memory references into how many cycles are there for the memory reference? In the question given 4 cycles. 4 cycles plus ALU operations. How many? 1, 2, 3. Only 3 ALU operations into 2 cycles. Register references not required because 0 cycles given in the question. So overall cycle time is 2 nanosecond. So this is the value. Okay na? So compute this. (16 into 4). 64 plus 3 into 2, 6. into 2 nanosecond. So this will be the answer. Compute the value. Right? So now when we observe the overall these two questions here, this is the interrupts related question, simultaneous and without simultaneous occurrence. This is the program execution which covers the all types of instructions, addressing modes, instruction cycle, interrupt cycle. So the overall concepts what we discussed till now, that will be covered in these questions. Okay, copy the questions and also copy the solutions. Copy it first. Next one is RISC and CISC architecture characteristics. According to the fixed length instructions and the variable length instructions designing, CPU architecture is classified into two types, RISC architecture and CISC architecture. Okay, so RISC means reduced instruction set computer, CISC means complex instruction set computer. These two computers are the opposite ends. That means when we know the characteristics of a RISC, opposite characteristics are true in the CISC. Clear? Right. Now first let us see the characteristics of a RISC computer. When we observe the RISC computer, it supports more registers. System with more registers. So it is coming under the register to register reference CPU organization category. So when it is a register to register reference CPU, all the operations are performed only on a register, so that register addressing mode is used. Altogether, in the entire CPU, number of addressing modes are less. First one, more registers. Second one, less addressing modes. Third one, RISC supports fixed length instructions. This is by default characteristic. When instructions are fixed length, system supports successful pipeline. Pipeline is successful only when the instructions are fixed length instructions. That we will see later. What is pipeline? Why it is successful only in the fixed length. Okay. Successful characteristics of a successful pipeline is CPI equal to 1. Successful pipeline characteristic is CPI 1. When CPI is 1, execution time is low, performance is high. Execution time is low, performance will be high. So RISC computer is a supercomputer. Supercomputer will be used in the super applications. Example, real-time applications. Okay. So RISC processor contain more registers. Register is a costly element. Therefore, entire RISC computer is expensive. RISC processor contain reduced instruction set. That means smaller instruction set. Okay. RISC CPU uses hardwired control unit design. We will see what is hardwired control unit later. Example of a RISC processor is PowerPC processor, Motorola processor, ARM processor. These are the characteristics of a RISC computer. Okay. Let me list out the characteristics of a RISC computer. More registers, less addressing modes, fixed length instruction, successful pipeline, CPI equal to 1. Supercomputer used in the real-time applications, expensive computer. Okay, smaller instruction set, using hardwired control unit, Motorola, PowerPC, ARM. Okay, these are the characteristics of a RISC. Opposite characteristics are true in the CISC. What are those? Here, RISC, more registers, less registers. Opposite, more registers, less registers. Less addressing modes, more addressing modes. Fixed length instruction, variable length instruction. Successful pipeline, unsuccessful pipeline. CPI 1, CPI not equal to 1. Supercomputer, general purpose computer. Real-time applications, personal applications. Expensive computer, less expensive computer. Smaller instruction set, larger instruction set. Hardwired control unit, microprogrammed control unit. Okay. Here example, Motorola, PowerPC, ARM. Here Pentium family processors. Like this, RISC characteristics and CISC characteristics are described. Understand? In the GATE exam, there may be a already questions are formulated. If you look at the previous papers, you can understand the concepts of the and questions of the CO subject. In the GATE exam, always numerical questions are not possible from this subject. Sometimes they will ask you, they will give the general statements and ask you to arrange the statements in a sequence to perform so and so action. So once you know the actions, you know once you know the actions and action oriented sequences, then you can answer such kind of the theoretical questions, conceptual questions. Okay, so be careful to understand all the concepts in this subject. Okay, so in this area, question is like this: generalized statements are given characteristics and ask you to identify the risk characteristics, or ask you to identify the CISC characteristics. Once you know these characteristics differences, then you can easily answer such kind of the questions. Okay, let me list out the characteristics of a risk. Here, characteristics of a risk. Full form is reduced instruction set computer. Now, first characteristic, it supports more registers. It supports less addressing modes. It supports fixed length instructions. It supports successful pipeline. Next, CPI equal to 1. It is a supercomputer. It is used in the real-time applications. It is an expensive processor. Next, it contains smaller instruction set. Next, it uses hardwired control unit. Example, Motorola processor, PowerPC processor, ARM processor. Okay, these are the characteristics of a RISC. Opposite characteristics are true in the CISC. See this. Characteristics of a CISC. Full form is complex instruction set computer. Okay, first one. It supports less registers. It supports more addressing modes. It supports variable length instructions. Okay, it supports unsuccessful pipeline. Right. Next, CPI not equal to 1. Next, it is a general purpose computer. Next, it is used in the personal applications. Next, it is a less expensive processor. Next, it contains larger instruction set. Next, it uses microprogrammed control unit. Next, example, Pentium processors. Okay, so these are the characteristics of a RISC computer and CISC computer. Very important characteristics. Please remember as it is, because these are the implemented systems characteristics. So we cannot add any extra point, we cannot delete any existing point. If we do that, the real system characteristics will be missing. System design will be misleading. So remember as it is, because these are not a hypothetical machines, these are already existed computers. So when these are existed computers, exact characteristics are supposed to be reported. So all those characteristics given here, remember them. Okay, copy it quickly. Copy it. Now next one is register organization in the RISC CPU. This we need to see. RISC processor supports more registers. So how the registers are organized in the RISC computer? Okay. Now, first point is RISC processor supports more registers. This is the first point. Second point is RISC processor registers are classified into four groups. Name as first one global registers, denoted with G. Second, local registers, denoted with L. Third one, in registers, denoted with C. Out registers, denoted with C. C stands for common. Common registers. In and out registers are the common registers. So in the RISC CPU, system supported registers are classified into four categories. You know? Right. Next one. In the RISC CPU, next point, in the RISC CPU, register window is formed. Register window is formed by grouping the local comma in and out registers. By grouping the local comma in and out registers. Right, look at this. So here this is the window. In the window C, L, C, like this. In registers, local registers, out registers present. You know, form the window by grouping local comma in and out registers. Fine. Next point is global registers are shared by all the register windows. Global registers are shared by all the register windows. That means global registers are common to all the windows. Therefore, window size equal to L plus 2C plus G. L indicates number of local registers. 2C matlab common in and out registers, C plus C 2C, and global registers are also shared by the register window. So total number of registers present in the window equal to L plus 2C, and global registers are also accessible here, so G. This is the formula used to calculate the window size. Cleared? And next one, why the window is formed like this and why registers are classified like this, so that will be present in the internal organization of a RISC computers. We are not going to examine the internal details of a RISC system individually. That is the reason we are not bothering about the how they are used in the application program. We are not bothering about that. Suppose we are reading only RISC computer, we need to post-mortem the RISC computer only. Then we can examine every parameter. But here we are going to take the overview of the RISC structure. So when we look at the overview, just architecture details are present. What is present in the architecture? But how to use every parameter, that will be explained in detail in the organizational concepts. Is it okay? So that's what we are taking, the just architecture view. In that architecture view, system supports more registers classified into 4 groups, named as global, local, in and out. By grouping local, in and out, form the window. In that window, global registers are also accessible. Therefore, number of registers present in the window is L plus 2C plus G. Is it clear? Okay. Next point is, in the RISC CPU, register windows are organized in a overlapping order. Register window organization is in a overlapping order. Overlapping means one window out registers are acts as a in registers in the another window. That is the overlapping. One window out registers are used as a in registers in the another window. In that order, all the windows are organized in the RISC CPU. Okay. Now let us see the concept here. See this is the window. Window 1, W1. What is present? In, local, out. Present na? Every window contain in, local, out. Now overlapping meaning is window 1 out registers are used as a in registers in the window 2, like this. So in the window 2, in, local, out. See, window 1 out registers are used as a in registers in window 2. Next, window 2 out registers are used as a in registers in window 3. In, local, out. This is the window 3. Is it clear now? That is overlapping meaning. Now window 3 out registers are used as a in registers in the window 4. W4. In, out, in, local, out. And so on. Let us assume the system with 4 windows. When 4 windows are considered, overlapping order means this. W2 is overlapping with W1, 3 with 2, 4 with 3. Got the point? 2 is overlapping with 1, 3 is overlapping with 2, 4 is overlapping with 3. Then what about 1? 1 is not overlapping with anyone. So it is an incomplete overlapping. To make it complete, it is the scenario like this. Now this is the complete overlapping. See, 2 is overlapping with 1, 3 overlapping with 2, 4 overlapping with 3, and 1 overlapping with 4. complete overlapping. Like this, windows are overlapped in the RISC system. And next one, apart from these registers, what we have on the top? Global registers, denoted as G. These global registers are accessible by all the windows like this. W1 using, W2 using, W3 using, and also W4 using. See this? Global registers are accessible by all the register windows. So this is called as the register organization in the RISC CPU. Okay, now we need to find out number of registers present in the RISC CPU. That is number of registers in the RISC CPU, denoted as register file size, equal to how many? W into, W stands for number of windows. How many windows are there? 4 windows. Into, in every window, how many registers are there? If you see every window, L plus 2C is there. Every window contain in, local, out. In, local, out. If you count like that, it is wrong count, because we are not talking about one window. We are talking about overall system registers. In the overall system, registers are organized in a overlapping order. Due to overlapping order, something is different here. The difference is, observe. See this. Let us count the local registers and out registers of W1. In registers are not counted for a while. For a while, don't count in. We will see it later. So count local and out registers of window 1. Counted. Okay, now comes to window 2. In the window 2, in registers, window 1 out registers both are same. When both are same, when we count the out registers in window 1, no need to count them into the window 2, because these two are same. So out registers are counted in the W1. No need to count them again into W2 as a in. So in the W2, we can count local and out. Okay, 2 registers. Because of W2 in registers, W1 out registers are same. Is it okay? Now come to the W3. W3 in registers, W2 out registers are same. When you count them there, here no need to count here. Now in the W3, local and out is counted. Got the point? So W3 out registers and W4 in registers both are same. When these two are same, no need to count the in registers in the W4. Count only local and out. Now come to this. See this. Window for out registers. Window for out registers and window 1 in registers are same. When window for out registers, window 1 in registers are same. If you count out registers in the W4, don't count the in registers in the W1. Job is completed. Is it clear? In this order, overlapping structure is present. Is it okay? That means what? In the overlapped organization, every window contain L plus C, not 2C. Either in registers or out registers. Don't count both because of overlapping. This is the total number of registers in this structure. Apart from this, what we have? Global registers for all windows plus G. W into L plus C plus G. This is the formula used to calculate the register file size. So W means number of windows, L means number of local registers, C means number of in or out registers, not both. G means number of global registers. Is it clear? So in this way, in the RISC computer, registers are organized. So in this concept, there is a possibility of two questions. That is, what is the window size and what is the register file size? So remember these two formulas. This is the window size formula and this is the register file size formula. By using these two formulas, we can directly answer the questions. Copy it. Copied. Okay, now question is, consider a hypothetical CPU which supports 32 global registers, 24 local registers, 12 in registers, and 12 out registers. Right? In the CPU, 40 register windows are overlapped. What is the size of a register file and window size respectively? This is the question. So CPU characteristics given, G value, L value, C value given, and a number of windows are also given. We need to find out the file size and window size. So when the characteristics are given in the question, just remember the formulas. When we remember the formulas, directly we can substitute the data to answer the question. Is it okay? Now substitution is, first, register file size equal to W into L plus C plus G. So W, how many? 40, L 24, C either in or out, don't take both, 12 plus G 32. Okay, now compute this, that will be the answer. Next, window size, that is L plus 2C plus G, substitute, L 24, 2 into C 12 plus G 32. Compute this. Got the point? So like this, in the question, complete characteristics are given. Okay, directly we can answer the question if we remember the formulas. Okay, na? So that is the way of answering the question. Fine. Up to now, computer architecture concept is completed. Is it okay? So till now, data representation in the computer is over and computer architecture is over. You are eligible to solve the workbook chapter 1 and chapter 2. Now practice these two chapters. We will see the analysis later. Is it clear now? Copy it. Now let us see the workbook chapter 2 analysis. Title: Machine Instructions and Addressing Modes. Here key given. First copy the key. Copied. Okay. So in this chapter, some questions we already covered in the regular class. So in the running notes, sample questions are available. By using those sample questions and the concepts, you can able to solve these questions. So let me explain questions in the sequence. Correct? Later I will address you which are the questions are covered in the running notes. See the question 1, question 2. This is a common data question. Program given. This is the program given. Okay, decrement L, decrement H. This is loop. This is first J and Z, this is second J and Z. What is H and what is L? H and L are the 8-bit registers. How we know 8-bit register? Because of H equal to 0 to H. That means 0, 0, 0, 0, 0, 0, 1, 0. That's it. L equal to 0, 5H. That means 0, 0, 0, 0, 0, 1, 0, 1. Like this. So H and L are the 8-bit registers. Right? Come to the execution. Execute this. First H equal to 0, 2. L equal to 0, 5. Decrement L. L become 0, 4. Non-zero. Next J and Z. Non-zero. Condition true. First time control transfer to L. L become 0, 3. Non-zero. Condition non-zero. True. Second time control transferred. L is 0, 2. Non-zero. Condition is non-zero. True. Third time control transferred. L is 0, 1. Non-zero. Condition is non-zero. True. Fourth time control transferred. L is 0, 0. 0 flag. Condition is non-zero. It is false. Then go to decrement H. H become 0, 1. Non-zero. Condition J and Z. True. When it is true, first time control transfer to loop. When it is enter into the loop, L is already 0. Okay, decrement, subtraction. You know that when the register satisfies the minimum limit, still when we are decrementing, value will be rolled back to upper limit na 2 minus 1, 1. All are ones. Means it become 255. Now L equal to 255. 255 means non-zero. Condition is non-zero. True. You know, control will be transferred. See this. Here L is 4. So 4 times control transferred na. In the fourth time condition become false. Now L is 255. That means what will happen? 255 times control transferred. Okay na? So in 255th time L become 0 na? 0, 0 means 0 flag will be set. Condition is non-zero, false. Then go to H. H become 0. Condition is non-zero, false. Go to sequence. What is the sequence after I6? Nothing is there. So stop prayer. Stop there. This is the way of execution. Decrement instruction invokes the subtraction operation. Means constant 1 is subtracted from the register or memory content. You know, when the register satisfies the minimum limit, value will be rolled back to upper limit. Is it okay? So that is the concept. Right? Then what is the question here? How many number of times first J and Z and how many number of times second J and Z transfer the control? है ना. First J and Z transfers the control to the loop 4 times plus 255. Total 259 times transfer the control. Second J and Z transfer the control only one time. Correct na? Now select the answer. Answer is, first question answer is C. And second question answer is A. Reason is decrement and subtraction. Both the operations are same but differ only in the carry flag. But here decrement operation controlled by the zero flag. Correct na? If you replace decrement with subtraction, zero flag behavior is same in the decrement and subtraction. That is the reason even we are using decrement or we are using subtraction in this program, output will be same, 259 and 1. Clear na? Question 1 answer is C. Question 2 answer is A. Then question 3, most relevant addressing mode for the position independent code. Answer is C, relative addressing mode. Conceptual question. Read the concepts which I explained in the regular class, present in the running notes. Okay, right, copy it. See the question number 4. Here question number 4 and question number 5 are the common data questions. Here program given. Right, this is the program given. Now we need to execute the program in a sequence to decide the answer. Fine. First, in the question given is A, B and C are 8-bit registers. Register size given 8-bit. Okay. Now see this. B equal to 0. C equal to 8. Next C 8 compare with 0. Comparison. After execution of the comparison, result will be available in the 0 flag and carry flag. That means second operand is compared with first operand. When both are same, 0 flag will be set. When both are not same, 0 flag is reset. So 8 and 0 both are not same, 0 flag is reset. Next, jump on 0. Condition is 0. Compare. False. When it is false, move to sequence. Now C become 7. RRC means rotate right along with carry. So A is a 8-bit register. A7, A6 like this. Rotate right along with carry means some extra storage space is present. So with that extra storage space, data will be rotating to right direction like this. This is the rotate right. After this rotate right operation, what is present? this is present. This is in the A register and this is the extra space. Okay, na? Then what is its meaning? Based on the status of this extra space, carry flag is set or reset. That means if A0 is 0, no carry. If A0 is 1, then carry. Carry flag will be set or reset based on the A0 bit. That means LSB bit in the A register. Clear na? Right. And next one, if you see these four instruction, jump on carry, JC, jump on carry, where the control is moving to Y location. So this condition become true. This condition become true only when the carry flag is set. Carry flag will be set when the A0 bit is 1. You know? When A0 bit is 1, carry flag is set. So condition will be true. When condition true, move to Y location. You know, in the Y location, B is incremented by 1. Then go to next iteration. When carry set, condition true. You know, increment B, go to next iteration. Carry will be set when the A register bit data is 1. Understood? Suppose A0 is 0. Carry is not present. No carry. Then what will happen? Condition become false. Then go to next iteration. Go to next iteration. And so on. So finally what is its meaning? During the execution of this program, A register data will be scanning bitwise. After every bit scanning, if bit is 1, B register is incremented. If bit is 0, nothing will be happened. So at the end of program execution, B register maintains the count of number of ones in the A register. Count of number of ones in the A register. Did you get the point? So this program will be executed 8 times. So A is a 8-bit register. In every time A data will be scanning. So see this. First iteration A0 is coming. Next iteration A1 is coming. Next iteration A2 is coming. Like that. In the last iteration A 7th bit will be scanning. See this. In the last iteration 1 is compared with 0, non-zero. So that here 0 flag. Condition become false. Then go to next. C equal to 0. Next this one A6. A7 is in the extra bit position. So if A7 bit is 0, no carry. A7 bit is 1, carry. When carry, increment B register. Go to next iteration. If no carry, nothing will be happen. Go to next iteration. In the next iteration, 0 compare with 0. Now 0 flag is set. Condition 0. When we compare this, true. When true, go to Z location. Sorry, go to X location. In the X location, what instruction is required to get the initial value? RRC A comma #1. Again, if we apply the rotate right, X is coming here, A7 is moving to the original place. So to get the initial value into the A register, put the RRC instruction here. Got the point? So objective of this program is reading the A register data bitwise. After every bit reading, B register will be incremented when the A register bit status is 1. So at the end of program execution, B register contains the count of a number of ones in the A register. Got the point? By using this logic, we can able to answer the question. So question number 5, question number 4, answer is B. Question number 5, answer is A. Okay, na? This is the analysis. I explained clearly. You know? Your responsibility is re-execute the program with this knowledge. Re-execute, re-analyze. Then you can understand the working nature of assembly language code. Clear na? Copy it After that, you please re-execute the code. Re-execute the code to get the perfection. Copy it quickly. See the question number 6. This is a theoretical question, so direct answer is C. Next, see the question number 7, question number 8, question number 9. This is a common data question. Okay, so program given here: I1, I2, I3, I4, I5. Size is given. Size, it is 2 word, this is 1 word, this is 1 word, this is 2 word, this is 1 word. Is it okay? So I5 is the halt given in the question. Consider that memory is byte addressable. Question number 7. Memory is byte addressable. Byte addressable means cell size equal to 8 bit. Okay, na? Now, in this, word size given 32-bit. 32-bit word means how many bytes? 4 bytes. Therefore, one word occupies 4 cells of a storage space. Program stored in the memory with a starting address of 1000. So 1000 is the starting address. I1. It is a 2 word. 1 word requires 4 cells. 2 word requires 8 cells. 1000 to 1007. Now instruction 2. 1 word, 4 cells. 1008 to 1011. Then instruction 3, 1 word, 4 cells, 1012 to 1015. Instruction 4, 2 words, 8 cells, 1016 to 1023. Instruction 5, 1 word, 1024 to 1024, 5, 6, 7. Next 1028 and so on. So valid program counters are the starting addresses of an instruction. Starting addresses of instruction is a valid piece. Then what the question stating? If an interrupt is occurred during the execution of halt. See this. Fetch cycle. Halt instruction is enter into a CPU. Program counter is increments to sequential address 1028. Now execution cycle. At the time of execution, halt invokes unconditional jump with the starting address of the halt as a target address. Because of it is unconditional TOC, without checking any condition, program counter sequential address is updated. Okay, na? Right. After execution, checking for the interrupt. CPU respond to the interrupts only after the completion of a current instruction execution. So interrupt occurred during the execution of halt, but CPU respond to the interrupt after completion of halt execution. At that time, interrupt occurred, PC value pushed into a stack. What is the PC value? 1024. Did you get the point? Yes, answer is 1024. At the time of fetching, PC increments to 1028. But at the time of execution, 1028 is replaced by 1024 because halt is a self loop. Next, question number 8. Consider word addressable memory. Word addressable, matlab cell size equal to word size. Okay, so 1 word instruction requires 1 cell space. 2 word instruction requires 2 cell space. So starting address is 1000. I1 is 2 word. So 1000, 1001. I2 is 1 word. 1002. I3 is 1 word. 1003. I4 is 2 word. 1004 and 1005. I5 is 1 word. 1006. Next 1007 and so on. This is the starting address of instruction, valid PC. Correct? If an interrupt is occurred during the execution of add, so which instruction is add? I3. I3 is a add. So see this fetch cycle. What is this instruction? ADD R2 R3. This is the instruction. fetched into IR. Program counter is increments to sequential address 1004. Now execution cycle. At the time of execution, R2 plus R3 result stored into R2. Execution completed. Is there any change in PC? No change because it is ALU instruction. PC is not updated in the execution cycle. Previously jump, PC is updated in the execution cycle. After execution cycle, checking for the interrupt. Interrupt is present or not? Present. When interrupt is present, PC value pushed into a stack. What is the value present in PC? 1004. And these two questions clearly shows the difference between jump behavior and ALU instructions behavior. During the execution cycle, program counter is not updated when the instruction is ALU instruction. Jump instruction updates the PC. Clear now? Next one. Question number 9. See the question number 9. What is given? I1. Instruction fetch and instruction decode together given. Next, processing. Instruction fetch and decode taking 2 cycles per word. Okay, na? So this is 2 word into 2 cycles, 1 word into 2 cycles, 1 word into 2 cycles, 2 word into 2 cycles, 1 word into 2 cycles. So fetch and decode takes 2 cycles per word. I1 is a 2 word instruction. So into 2 cycles. Total how many cycles? 14 cycles. Count them. Next. I1 is data transfer from memory to register. Memory to register taking 3 cycles given in the question. I2 memory to register 3 cycle. I3 addition 1 cycle. I4 register to memory 3 cycles. Then I5 halt, no need of any cycle. So total time is how much? 10 cycles. Is it clear? Now program execution time is 14 plus 10, that equal to 24 cycles. Is it clear now? Like this we can calculate the execution time of a program according to the given data. And data given, accordingly we identified this. Fine. So 7th question answer is C. 8th question answer is B. And the 9th question answer is B. Analysis is this. And already you know the concepts of interrupt cycle, instruction cycle, byte addressable memory, word addressable memory, etc. By using those concepts, questions are formulated like this. Fine. Next, question number 10. It is a theoretical question. Answer is C. See the running notes to get the picture. Question number 11. Already we calculated. Answer is C. Question number 12. Answer is C. See the running notes to get the image. Then question number 12. Answer is C. So see the concepts which are explained in the running notes. Addressing modes concept. In the running notes, all the addressing modes are covered nicely. Therefore, see the running notes, addressing modes information to get the complete picture of a addressing modes. With that addressing modes, you can answer the 12th question. Answer is C. Okay, na? Now read the question number 13 and 14. Read the question number 13 and question number 14. Okay, these questions are common data questions. These questions are common data questions. Read the questions. Completed? Very good. These questions uses the expand opcode technique. Expand opcode technique. You know that I already explained expand opcode technique in the classroom course. That is regular computer organization concepts. Also we solved so many questions, right, based on the expand opcode technique. So let me recap the concept in this question. Later you can use this information to solve the remaining questions which are formulated based on expand opcode technique. Okay. So in this system supports what is given 16-bit instruction. Instruction size is fixed. Formats are 2 address format and 1 address format. Different instruction formats on a fixed length instructions that become a expand opcode technique. Okay, right? Now, what is the 2 address format? Opcode, address 1 and address 2. Okay, what this is a 16-bit instruction. Address size 128 word log 128 base 2, that is 7-bit. Log 128 base 2, that is 7-bit. And rest how many bits are there? 2-bit opcode. Then 1 address instruction, 1 address format, opcode and only 1 address. So 7-bit address required. Another 7-bit address we don't want. So merge with opcode. Then opcode length is increases. That is expand opcode technique. Clear? So this is 2-bit opcode. This is 9-bit opcode. Therefore this is a primitive instruction. And this is a derived instruction. Got the points? Very good. Now apply. Take the primitive instruction, that is opcode, address 1, address 2. Seven bit, 2-bit. Next, number of operations possible equal to 2 power 2 means 4 operations. When we are going to answer the 13th question, what the question stating? Range of 2 address and 1 address. We don't know how many 2 address instructions are existed. Range we need to identify. So share the opcodes. Share the opcodes between 2 address and 1 address. Is it clear? Okay. So share means minimum to maximum. Total is 4. First, minimum 1 address instructions 1. Maximum 3. 3 opcodes are free. Maximum 2 address 3 and 1 opcode is free, like this. Minimum 2 address instructions are 1. 3 opcodes are free. Maximum 2 address instructions are 3. Free opcodes are 1. Therefore, range of 2 address instructions equal to 1 to 3 and range of 1 address instructions equal to minimum free opcodes are 1 into address 2 to the power of 7 to maximum free opcodes are 3 into 2 to the power of 7. Okay, na? So that is the answer related to the 13th question. Okay, na? Select the option B. Minimum free opcode is 1, merge with address. Maximum free opcode is 3, merge with address. Next, question number 14. Number of free opcodes after allocating the existed instructions. How many 2 address instructions are possible? 4. How many existed? 2. So that only 2 free opcodes are there. Those free opcodes are used for 1 address instructions. So number of 1 address instructions possible equal to free opcodes 2 into merge the address, that become 256. Answer is C. Okay, this is the expand opcode technique. Already you know the expand opcode technique. You solved so many questions in the class. By using that concept, analyze this question. I already given the explanation. You please re-evaluate to get the perfection. Clear? Right. Next question. 15, 16 and 17. Next question is 15, 16, 17. So common data linked questions. Common data linked means data is common. Link means there is a relation between the question to question. Fine. If you look at this question, common data format says 40-bit instruction. We have one register operand and one memory operand present given in the question. Memory capacity 256 MB. So log 256 mega base 2, that is 28-bit address. Registers 128 base 2, that is 7-bit address, and rest 5-bit opcode. This is the common data. When students are going to answer this question, directly they are saying 5-bit opcode, 2 power 5 operations. But that is not correct. Reason is we need to read the question. Common data says this. After that, read the question. How many different operations the computer can perform if indirect bit is used as a part of opcode? If indirect bit is used as a part of opcode, that means in this 5-bit opcode, we have a opcode and addressing mode. So how many addressing modes? One addressing mode. To represent one addressing mode, 1 bit required. Therefore, in the 5-bit, 1 bit is reserved for addressing mode. Total how many bits are left for the opcode? Only 4-bit. 4-bit means number of operations become 2 power 4. That is equal to 16. This is the answer. Did you get the point? Number of operations possible is 16. But student mistake is they are saying 2 power 5, 32. But answer is 16. Got the point? So, question number 15. Answer is B. 16. Expand opcode technique. 17. Expand opcode technique question. You please solve the 16 and 17 based on the expand opcode technique concept. So answer is B and B. Okay, now 18th question. If you see the 18th question, memory location 1000, memory location 1001 and memory location 1020 contain 18, 1, 16 respectively. Okay, we are executing the code I1. Move immediate. So RS equal to 1, constant 1 moving to RS. Now I2. It is load using the index addressing mode. See this? RD loaded with memory content of 1000 plus RS. Now RS contain 1, adding with 1000, 1001. Memory content of 1001 is 1. So RD equal to 1. Now I3. Add immediate. So RD loaded with RD plus 1000. 1000 is a constant. RD contain 1. Adding 1001. Now this RD is 1001. Okay. Now I4. In the I4, store 0 of RD. That means memory content of 0 plus RD. Updated with 20. 20 is a constant updating into the memory. So R of D, what is there? 1001. Adding with 0. 1001. Memory location of 1001 contain 1. Now that 1 is changed to 20. So at the end of execution, memory location 1001 contain 20. Got the point? So answer is D. Like this, analyze the questions which are related to the instruction, formats and the addressing modes. Okay, practice like this. By looking at the question, you can able to execute the question. You can able to understand the question, what the question it is, means what type of instruction it is, what type of addressing mode is possible. Accordingly, you can execute I1, I2, I3, I4. Final answer is memory location 1001 contain 20. Is it clear? Copy it. See the question number 19. Okay. Here, register R1 data transferred to memory. Then memory to data transfer to R2. Then again memory data transferred to R3. What is the necessity of accessing 3 times memory? When R1 and R2 and R3 all are present within the CPU, first forward the data internally, later update the memory. So this we can replace like this. R1 data transferred to R2, R1 data transferred to R3, then R1 data transferred to memory. Then number of memory references are reduced, performance increased. Correct answer is D. Then question number 20, answer is D. Question number 21, answer is D because of theoretical questions. Question number 22, answer is B. Question number 23, again, and answer is C, theoretical question. Question number 24, answer is D. We computed this, na? Register file equal to W into L plus C plus G. This is the formula. Now question number 25, answer is B, D. Question number 26, risk and CISC characteristics already known to you. Answer is A. Question number 27, answer is D. Because of RFE, return from exception is equivalent to return from interrupt. Return from interrupt, or else we can say return interrupt return. So every interrupt subprogram must be end with interrupt return. It must be a privileged instruction. There should be a valid opcode required for the IRET instruction. While execution of IRET instruction, no other interrupts are entertained. So answer is D. Question number 28, C. Question number 29, structure. Structure is a heterogeneous data element set. So you may access any member of the structure randomly. So when we are going to access any memory data randomly, indexed addressing mode will be used. Linear order, auto indexed addressing mode is used. So when we want to access random element from the memory, indexed addressing mode is used. Answer is D. Question number 30. Question number 30. So here, program given. "25 statements program given. In the 25 statements program, X is assigned to new value in the 6th statement, 9th statement and 12th statement. Here X is assigned to new value. Later, X will be used as a input. X will be used as a input in the 7th statement, in the 8th statement and in the 10th statement, in the 16th and 17th statement. Given like this. Then statement ranges where the register used by variable X could be assigned to some other variable. Whatever the register is used by the X variable, the same register is used by how many other statements? How many other statements are using the same register used by the register variable X? Say this. First time in this program execution, register 1 will be allocated to X variable during the execution of 6th statement. first time register will be allocated to the X variable at the time of executing the sixth statement. And next, seventh statement using this X as a input, producing the output. Now, is that output stored into the register 1? Is that output stored into the register 1? If you want to use register 1 to store the seventh statement output, first verify what is there in the register 1. What is there? X is there. Is this X required in the future? Required. Where? In the 8th. Therefore, don't replace this X. Go to register 2. Store the result of 7th statement. Next, 8th. 8th statement using this X as a input, producing the output. Now, shall we use this register to store the 8th statement? This X is required as a input in the 10th statement, but this 10th statement X is new X. Therefore, this is replaced with 8. Now, 9. 9th statement executed, it brings the new value into the X. Now 8th is not required, so 9th statement is present. Because of 9th statement, again X is coming here. Understand? Now 10th statement using this X as a input, producing output. Shall we use the same register? Yes, you can use, because X is acting as a input, but that is new input. Correct na? Generated by 12th statement, but this X is generated by 9th statement. So this is not required, replace. 10th output, shall we replace with 11? You can replace, because 10th output not required. 11th output, shall we replace? Yes, you can replace with 12. Again X came. This X is required in the 16 and 17, then don't replace. So execute the 13, 14, 15, but here you can store. Don't replace the X. Now 17, this X is used as a input. Output is there. Shall we replace this X? No. Why? This X is required for the 17. So here. Now 17, using this X. Okay, now after that, do you want any X here? No. Therefore, this 12 is replaced by 17. 17 by 18 and so on up to 25. Statement ranges. Statement range of statements which are using the same variable which is used by X, which are using the same register which is used by variable X. X is a variable using the register 1. The same register is used by 8th statement, 9th statement, 10th statement and so on. According to this, answer is A. Register reusability. Actually, this concept, before reusing the register, take the existed data in the register and verify whether that data required in the future or not. If data is not required in the future, replace the data. If data is required in the future, don't replace the data. By using this logic, we can able to solve the question. Register reusability. Before replace the register data, take the data and verify the program whether that data required in the future or not. If required, don't replace. If not required, replace. By using this logic, we can solve the question. Got the point? Next. Question number 31 and question number 32. These questions we already solved in the classroom. So no need to solve this. You please verify. Solution is B and D. Okay. Then question number 33, question number 34, question number 35. These are the common data questions. Common data. Program given here. See this. Memory location of 3000 contain 10. Memory location of 2000 to memory location of 2009. Initialized with 100. Okay. Now, program starting address is 1000. This is the question. Memory content of 3000 is 10. Memory content of 2000 is 100 up to 2010 na 2000 to 2010 memory cells contain the value 100. Program address is 1000. Now program given here. Program given. What is the program here? One, two, three, four, five, six, 7, 8. Total 8 instructions present in the program. 1, 2, 3, 4, 5, 6, 7, 8. Okay, na? So this is the B and Z instruction. To loop. Loop is located here. This is the halt instruction. Very good. Right? Now, so in this program, write the program completely. Move R1 comma 3000. This is direct addressing mode. Move R2 comma R3. Register indirect addressing. Add R2 comma R1. Then move R3 comma R2. Then here increment R3. This is decrement R1. Okay, this is the program given. Now see this, actually here memory content of 3000 loading into R1. Now R1 become 10. Now here, what is its meaning? They given memory 2 square brackets enclosed with R3 loading into R2. R3 contain, in the question given, R3 contain 2000. So 2000. Memory content of 2000 is 100. Memory content of 2000 is 100. So finally R2 equal to 100. Next, add R2 plus R1. So R2 equal to 110. Then move like this. R3. R2. R3 contain 2000. So 2000 already contain 100. Now that is replaced with 110. So now memory location 2000 contain how much? 100. Now that is replaced with 110. This is reading and writing. This data reading and also same data writing. Next increment R3. Now R3 become 2001. Then decrement R1. R1 become 9. 9 is non-zero. Now condition is non-zero. Control will be transferred. That means this loop body will be running 10 times total. 10 times loop body running. So in the first time 2000 cell data reading and 2000 cell data updating. Second 2001 data. Next 2002 data. Like this 10 iterations. 2000 to 2009 cells of information will be updated. No change in the 2010 cell. Okay. What the question is? How many memory references are required to fetch the data completely? How many memory references are required to fetch the data completely? Is it clear? Now see this. This is 1 MR. This is 1 RR, 1 MR. Here 1 MR. Is it okay? 1 RR, 1 MR. Here there is no MR. Data ke liye. We are concentrating on the data related memory references. Now you tell. This loop body executing how many times? 10 times. So within the loop body 2 memory references. So total memory references to access the data in the program equal to 1 MR outside the loop body, 2 MRs inside the loop body, that is executing 10 times. This is equal to 21 memory references. Is it clear now? And next one, in this program execution, in the program execution, 10 memory cells are accessed. That is 2000 to 2009 cells of information is accessed. Therefore, no change in 2010 cell. So 2010 cell contain 100 only. That is initialized with 100. That same 100 will be present. Got the point? So question number 33. Answer is 21. 34. Answer is what? 100. Now what is the 35? See the 35 question. Read the 35. Assume that memory is a byte addressable. Word length is 32-bit. Interrupt is occurred during the execution of increment. What will be the return address? So question number 35. See, byte addressable storage. Byte addressable means cell size equal to 8-bit. Is it clear? Right. Now, instructions are in the word format. Instructions are in the word format. Correct na? So what will be the word size? Given in the question 32-bit. 32-bit means 4 bytes. So one word requires the 4 cells of the storage space. Now storage. Program will be stored from 1000 location onwards. I1, 2 word, 8 cells, 1000 to 1007. I2, 1 word, 4 cells, 1008 to 1011. I3, 1 word, 4 cells, 1012 to 1015. I4, 1 word instruction, 1016 to 1019. I5, 1 word instruction, 1020 to 1023. I6, 1 word instruction, 1024 to 1027. Next I7, 2 word instruction, 1028 to 1035. I8, 1 word instruction, 1036 to 1039. Next 1040 and so on. This is the program storage. What the question? Interrupt is occurred during the execution of increment. Increment instruction is, see this, increment instruction is I5 instruction. See, this is the I5. So, fetch cycle, increment instruction, increment of R3. This instruction is fetched. Program counter is increments to sequential address 1024. Now go to execution cycle. At the time of execution, R3 will be incremented. After execution, check the interrupt. So CPU will be respond to the interrupt only after the completion of a current instruction execution. After completion of increment instruction, CPU checking for the interrupt. Interrupt present or not? Present. Now immediately PC value pushed into a stack. What is the PC value? 1024. Did you get the point? 1024. Completed now? Now answer is 1024. Okay? Correct. So analyze the questions like this. See the question 36. Right? 36th question contain the instruction ADD A of R0 at the rate of B. This instruction is a 3-word instruction given. 3-word instruction. It is in the IR. So operation is addition. This is the source 1 and destination. This is the source 2 explained in the question. What is source 1, what is source 2 and so on. Source 1 destination using index addressing mode. This is also given. And source 2 using indirect addressing mode. And B is a memory address, therefore memory indirect. So take the fetch cycle and execution cycle. Fetch cycle IF, ID execution cycle, OF, PD, WB. OF source 1 and source 2, WB destination. Now see this. IF 1MR to fetch the first word. After fetching the first word, opcode is available. So decoding the opcode, CPU came to know that operation is a addition. It is a 3-word instruction. Therefore, 2 memory references required to complete the instruction fetch. Then source 1, index addressing. So 1 RR, 1 ALU, 1 MR to get the data. Source 2, memory indirect addressing mode, 2 MRs. 2 MRs. Then PD, 1 ALU operation. Destination index addressing mode, 1 RR, 1 ALU, 1 MR. Like this, instruction execution is takes place. Understand? Now what the question? Number of memory cycles needed during the execution cycle. They're asking only execution cycle. Count these. How many? 2, 1, 2, 1. Answer? 6 memory references required in the execution cycle to execute the above instruction. Instruction is a 3-word long. So 1 word fetch is happened in the fetch cycle. Remaining 2 words are fetched in the decoding cycle. Because of opcode is decoded, CPU can understand the length of instruction as 3 word. Therefore 2 memory references are counting under the decoding state. Okay. After that, source 1 addressing, source 2 addressing, destination addressing, you know. Accordingly, these are the actions. So answer is how many memory references? 6 memory references. Cleared? Right. Next question number 37. Expand opcode technique question it is. You know what is the expand opcode technique, how to use it. Okay na? Solve it. Answer is given here. See this. Then question number 38. This is instruction format question. Already we covered instruction format related questions. Use that knowledge and solve it. And question number 39 and question number 40. These two are following the common data linked questions. Okay. What the question stating? There is a 3 byte long instruction. Instruction is 3 byte long. Stored in the memory with a starting address of 342038. Decimal addresses. Okay na? Now during the fetch cycle, instruction will be transferred to CPU. IR. Now program counter is increments to sequential address 342041. Now this is undergoes execution. Opcode and address field. Address field contain -31. What is this opcode? PC relative jump. Okay, this 31 is the relative value. Because of it is PC relative jump, effective address equal to PC plus relative value. Okay na? PC 342041 plus relative value -31. Then answer is 342010. This is the effective address. -31 is the relative value. Opcode is a PC relative. Effective address is PC plus relative value. Did you get the point? Next one. Same story. This is the question number 39. Analysis. PC relative addressing mode. Then question number 40. What is the point? I1 is fetched from the memory to CPU. Same connection. Linked question. Now program counter will be 342041. Now what is this I1? Opcode and -31. This opcode indicates the base indexed relative addressing mode. Addressing mode jump. So this will be the relative value. Address will contain relative value. Now effective address equal to R subscript B plus R subscript I plus relative value. Is it clear? Base register plus index register plus relative value. So base register contain 480220. Index register contain 9. Relative value minus 31. Now compute this 480198. This is the effective address. Already addressing modes concept is covered in the classroom in detail. Use that concept, re-evaluate the question. Then you may understand the concept clearly. This is the PC relative jump and this is the base index relative jump. The way of calculating the effective address is this. Question is clear to you? Okay. Copy it quickly. Copy it. Copied. Now question number 41. In the 41 question, tree given. This is the tree. Expression tree given. In this tree, variables are present in the memory. Variables all are present in the memory given in the question. Operators are accepting the operands only from the register. Only from the register we are accepting the data. Only from the register accepting the data to manipulate. But if data is not in the register, they are in the memory. Variables are in the memory. Operators accepting the data from register. So first transfer the data from memory to register. After the processing, result is present in the register only, given in the question. After the processing, result is present in the register. No intermediate result stored in the memory. No spilling. Without spilling, executing. Got the point? How many minimum number of registers are required? Answer is, evaluate this expression from bottom to top. When tree is given, execute from bottom to top. When program given, execute from top to bottom. Now see, first use R1 to get the C, R2 to get the D. Now adding R1 and R2, store the result into R1. Why? In the R1, C is there. This C is not required in the future. That's what I replaced the C with the result. Come to this one. I want to get the E value from the memory. Use the register. Which register? Can I use R1? I cannot use because R1 data required for the subtraction. Can I use R2? Yes, you can use because in the R2 D is present. D is not required in the future. So R2 minus R1 result stored into R2. E is replaced because E not required. Next, come to this side. Use R1 to load A. Can I use R2 for B? No. Take new register R3. Then R1 minus R3 result is stored into R1. Any one of the register you use R1. Now here R1 plus R2 result is stored into any one of the register. Use R1. So how many minimum registers are required to evaluate this? 3. Got the point? So register reusability concept, which we already used in the chapter 1 only. Question number where we used that. At the time of solving question number 30, register reusability concept is used. Same concept here. Before replace the register data, take the existing data from the register and verify the program whether this data required in the future or not. If required, don't replace. If not required, replace. This is the register reusability. When we are reusing the register, number of registers will be minimized in the program execution. Got the point? Use the same concept, solve the question number 42. but here program given, execute the program from top to bottom. You follow the same register reusability concept, then answer should be 3. Practice this register reusability concept. Then question number 43. Here different addressing modes given. Frequency means percentage, how many instructions are designed with register addressing, how many are designed with immediate addressing, the complete frequency given. We need to calculate the average operand fetch time. Average means sum divided by count. Whenever information is in the percentage, adding the percentage relative value equal to 100%. So count become 100%, 1 average equal to sum only. Now tell me, average operand fetch time equal to, tell. 30% of instructions are register addressing mode. When the data present in register, 0 cycles consumed. 20% of instructions are immediate. Data present in instruction itself, 0 cycles required. Question indicated that. Plus 22% instructions are direct addressing, 1 memory reference, 3 cycles. 2 cycles consumed. 1 memory reference, 2 cycles consumed. Next, 17% of instructions are direct. Direct means memory indirect, 2 memory references. 1 memory reference takes 2 cycles, 2 memory reference takes 4 cycles. Plus 11% of instructions are indexed. 1 RR, 1 ALU, 1 MR. RR 0, ALU 1 cycle and MR 2 cycles, total 3 cycles. Right? Compute this. Compute. And computational output is 1.45. Average operand fetch time is 1.45. Because question contain the addressing modes and the cycles required to access register, to access memory and to perform the ALU computation. Accordingly, average means sum divided by count. Count is a relative value 100%. Average equal to sum only. This one. Okay, na? This is the end of chapter 1 analysis. Sorry, chapter 2 analysis. In machine instructions and addressing modes, chapter analysis is completed. So you please practice the questions based on the concepts which I explained in the classroom and also analyzed in the workbook. Okay, na? So re-execute all the questions in this chapter. Then your concepts will be perfectly sitting in the brain. Got the point? Because concepts are very important. To develop the confidence in the basic concepts. So you please re-evaluate all the questions in the chapter 2. Chapter 2. Addressing modes and instruction set questions. Is it clear now? Copy it quickly.